Well, that's all I can wait. It's been all week. I've been dying to see this intentional software thing. We have Magnus Christerson, who is the VP of Software Development at Intentional Software, and we have Shane, who I know nothing about at all. So I imagine I will learn when you learn. Please welcome Magnus and Shane.
Thank you. Hello, thanks for having us here. It'll be a pleasure to present this. Now, we've heard here a lot about parsers, domain-specific languages that are textual versus graphical. We've looked at a lot of code here. And what I like to do is to put the word domain back in domain-specific languages. We're going to focus here today a lot about more on the domain. What is the domain and how do we express domain? And I think if we would have a domain expert in this room over the last 2 days, they would be totally confused on who we're talking about. In our mind, the domain has a language already. It's the domain of it's the language of the domain experts, and of course they know what they want to express. And I think one of the big problems in software development is that we force ourselves to express their domain knowledge in software code, and we all know that's just a horrible match. Just impossible to express rich domain knowledge into software code. It gets scattered across the code. It creates this accidental complexity. A domain expert has no idea what we're talking about. They are just trying to answer the questions that they think are random from their perspective. So what we're trying to do at Intentional Software is to start from the other angle, saying what do these domain experts want to express? What are the domain knowledge that we need to capture? And then work backwards from that. We don't start with a parser. We don't start with a grammar. We start from the other direction. If you would think back, say, 50 years in the software industry, the 50s, early 60s, and look at the work they were doing at that point in time, of course they needed a way to feed the instructions to the machine, and the way they did that was punch cards. So of course you needed a parser to process the punch cards in. But if you think about the computing paradigms today, we don't need punch cards anymore, and still we feed the tokens to the compiler. So I think there's something that went wrong over the last 50 years. So we're trying to radically rethink how could this process work much better if we took a radical and fresh approach to it. So what we're trying to do at Intentional Software is to create an environment, and we use the word domain workbench to build on Martin's definition of language workbenches, but we focused on the domain and find a processable representation of domain knowledge. And I say processable, not computable here. So this is not necessarily Turing complete, but we can process the knowledge. And we try to find, is there a way to express this knowledge in a way that can accelerate the software innovation we need? And can we use these intentions from the domain experts to get to the software? And let me go through a little bit about what is the background here and what are the things we need to express. So in a software project, we typically have these two key players. A domain expert that are very precise in their domain. They know exactly what they want to say, but they don't know how to express it in the words of the programmer. The programmer, they are very precise in what the instructions that they need to give to the computer to be able to execute something on a machine. And of course, these two are notion of precision and expression is very, very different. So the trick here is to find a combination of bridging or eliminating the gap between these two. The programmer, if we look at the x-axis here, he's worried about computing power, and at some point we pass this Turing complete executable languages that can execute on a computer. On the other axis here, think about the domain abstractions. The business expert typically care about the business domain, and typically they are not expressing themselves in an executable language. So if we map the tools they use in these quadrants, we find that most of their work goes on in these two quadrants. And of course, this is where a lot of the domain knowledge exists today in the organizations. And of course, this is today not very processable. Yeah, you might be able to print it, but that's about it. Yeah, you might be able to analyze some stuff in Excel, but it's not very useful and precise input for the programmer. What we're trying to build in the domain workbench is a way to bridge these two domains, a way to express this type of information in a way that we can map it into a domain definition that can be mapped and transformed into something that's computable. Now, of course, that's a tall order, so let's see how we're doing that. In the old world, when we talk about programs, we mean the software is the program here. So there is something that the computer needs to run. And the programmer creates that list of instructions. And the domain expert, they typically have some other notation or some other expression of their domain expertise that they are typically maintaining in different files than the software code. And of course, they need to explain this to the programmer, and there's back and forth among these two. In the new world of the intentional software idea is that how can we create an environment where these two key players can collaborate? And the way they collaborate is that express the domain knowledge in the way that's suitable for the domain expert. Start from the domain expert's own domain and find the most natural notation for the domain expert. Then create an environment that processes this, transforms this into something that the computer needs to chew on. So the output is the same as before, but the way the process works and the way we define what is software is very, very different. In this word, the software means the domain knowledge and something that processes that domain knowledge. And this might be a little abstract for now, but let's look a little bit into why is intentional different. We have a very, very clear way to separate these domains. And typically a business domain might be composed of multiple different subdomains. So we clearly separate the domain problems, and typically there are multiple domain expressions here, separated from the programs. We also describe how the program is generated, not what it is. For people that are familiar with complexity theory, you might have heard about the Kolmogorov complexity. This is exactly what Kolmogorov complexity is about. How it's a way better way to describe how things are grown rather than how they are, what parts they have. Because our DNA works in the same way we grow a body. The DNA doesn't describe a body. The domain representation, as I mentioned, doesn't need to be computable. In most cases, it's not computable. But we can process it into something that is computable. Of course, this idea of do we have textual or graphical DSLs is totally rubbish. The domain expert, who cares? I want to express what I want to express. In my domain, there might be a combination of these. So we have to allow graphical, textual, or symbolic notation. We have to raise ourselves to just not worry about ASCII anymore. We edit these domains directly in the environment, and we don't do any parsing. We don't import text strings or punch cards anymore. And we, of course, have to mix multiple domains. So in a typical business domain or a technical domain, there are dozens of different domains that need to collaborate. So the idea of having domains be integrated and work together is extremely important. So if you look at this domain workbench we've been working on for a long time, so what are the main requirements? Well, first, domains must be easily transformable. So this needs to be a very, very clear way to transform domains into each other. Any customer notation must be acceptable. We need to be able to mix domains. Domains must be able to evolve without limitations. And this is something I mentioned last night in the panel discussion. These domains will rev much, much faster than what we used to from programming languages. And this includes both the structure, or what do we want to express, and what is the notation we want to use to express those intentions. And we also need a common editing environment for these things, as well as something that I haven't heard anyone discuss is groupware. How do we expect domain experts collaborate with each other and collaborate with programmers? So groupware is a very, very important aspect of this type of environment. So looking from the inside, and what are the main components here. So at the core, we have something we call the intentional tree. This is what Martin called the semantic model. This is not an AST. We could express ASTs in this, but it's way broader than that. This is where we capture a lot of the data about the domain. We use projectional editors to project it both actually to the programmer as well as to the domain export. And they edit their domain code in the notation that they like. And of course, this projection is then bidirectional. So project things here, we do some editing, and that goes back to the intentional tree. On the back end, there might or might not be something that transforms this into regular code. Of course, this is a semantic model, so this we could write an interpreter for this. We can evaluate this directly, and we'll show some examples of that later on. The parser intentional tree, a little bit about what that is. This is a pretty unique data structure that has a uniform representation for all the domain code we want to express. It has strong identities throughout, as opposed to an AST or meta models or database schemas or XML document. There's no fixed meta levels. So a node can reference other nodes. Like here I have an example of a return statement. So an assignment has a definition. What is an assignment? Or what is a division? And then I can define these as in terms of other more primitive definitions. So actually we have version storage, so all the nodes in the tree is versioned. The tree itself doesn't comply to a grammar or to a meta model, but each node in the tree knows what type of node it is. So we've separated these concerns in terms of what is the data versus what is the definition of that data. Yeah.
The data structure here, so it can go off and reference all kind of stuff. So really, it's more of a complex graph.
Yeah, it's correct. So there is kind of a primary structure, which is trees, but you're right. There's lots of cross references in here. The projectional editing is very useful because it separates the representation from the surface notation that we see on the screen or in an output. And as I mentioned, this works in two directions, both editing as well as a display. And as we're manipulating the tree here, or the semantic model, we need to have special editing operations. And we'll show a little bit of that in the demo here. We have in the system there's a large number of notations to match any existing notations. Tables, graphs, text, curly braces, if you like that, and so on. And of course, we need to match and be able to mix the different domains. So we might have a domain that's graphical combined with something that's more table-oriented, combined with some more textual-oriented. And of course, it has to be resolved ambiguities, because we're not parsing here. We have a much freer way to express ourselves, and there cannot be any ambiguity what we do edit. And of course, the domains has to be able to evolve very rapidly, independent of each other. We also use the same environment for editing the programs and the schemas and so on. And we'll show a little bit of that too. So I'm going to ask Shane, who is our engineering director here in Bellevue, a few miles down the road, and he's going to help me walk through a demo of how to use this system and how to program this system. Let's see if we... The examples I have in the slides, I had to send in the slides like everyone else a few weeks ago, and Martin brought this state machine example up. So we said, well, what the heck, let's just do a state machine. So here is a program that defines a state machine. It's very straightforward. We define a domain def, a state machine, and a state machine is a machine programming machine. It has states, it has events, it has commands, and so on. And the state has transitions and actions. Very, very straightforward. Nothing unique here. What's interesting is that we're now looking at a projection of the tree that defines this. So, Shane, why don't we select this whole state,
okay,
def state, and look at the native. So if you peek under, what are we actually looking at here? So if you go into a native here, which takes away all the surface syntax, this is actually the tree underneath. Or it's a projection of the tree that's more native than the real thing. We don't see grids and stuff like that here. But
you never get to see the real thing.
Yeah, right. The real thing exists in your mind only. So of course, we don't see semicolons here, for instance. Semicolons, since like Gilla, we're also going to take over the world. We actually apply semicolons in the projection, not in the real thing.
And curly braces.
And curly braces, yeah. So let's go back to the C-sharp-like notation here. But yeah.
Projection, is this supposed to be the language of the domain?
No. So this is this programming language here is we can say domain-specific language to program the domain workbench. So the user here is a programmer, and they like curly braces. That's why we added a lot of curly braces here.
In your graphs, you had the projection, and
Yes.
you project
Yes.
the domain
Right,
expert. I
right.
thought that's what you were doing. Just
No,
Well,
we are
in
build.
this case, you can think of the domain expert being the domain creator, the programmer.
Yeah.
And so we're actually projecting the language for building building workbenches, which is this actually a collection of domains.
So we're still in the programmer role, building a state machine environment for a domain expert.
So the domain def is the model, and the definitions are different concepts in that model.
This language here is actually an extension of C#. So we have C# in here. We can actually scroll down a little bit. Let's find some computation that goes on somewhere. Let's look at some transformation that uses native code. Here's an example. A command that uses a bunch of pretty standard C# code. So we've added a bunch of keywords to C# to be able to make it more intentionally what we want to express. So we're embracing and extending C# here. So scroll back. What we have more we have a bunch of domain definition that defines the schema. And then we add, let's say we have a number of transition. This is still the domain definition. We have a bunch of domain definition that we're going to transform this to text and Ruby and so on. But let's scroll down and look at some transformation of projections here. Here's some projections. Why don't we look at how to write projection between the domain code and the screen here. Here's a very straightforward projection. We're saying, well, it's projections implemented for the state machine language. And we're going to have project events. And we're going to project events as the table. And we're going to have a header, we're going to have rows, we're going to have columns, and that's it. That's how we're going to project events. Here we're going to project commands, and it's, again, very declarative. So I want to project those as a table, and so on. Here's a machine program. We're going to project it as a property sheet, and it's going to be a tree-like, not a sheet-like. So it's I'm going to use these styles, and so on. So it's very, very intentionally how I describe my projections here. Let's look at some transformations. So for each of the elements in the schema, I define these projections. Then transformation. Here's how we transform, in this case, the state machine language to code. I define a few transformation here for the machine-machine program. This is an example where, rather than having a declarative way to transform this, I'm actually going to write C# code. So here, from this on, vanilla code here.
With some quotes mixed in.
The boot code?
The quotes, yeah.
So in this case, we're actually going through it for each loop. And in this case, we would, whenever you come in here, just add this to the intentional tree.
I have a quick question. You have a number of these, as it says, unnamed projections. You define project as project fields. Is there some naming scope or?
Let's look at one of them. The way it works is that we haven't given this guy a name yet. We say it's implemented for SML, State Machine graph. So yeah, we could probably put that
Yeah,
more.
what you're saying
somewhere.
is a not very good projection in our table of contents.
But for example, I see project field events, and I'm going to presume that that's referencing project def event in terms of a scope reference.
Project field events, that guy.
Like this one.
And how does he relate to project def event?
So project field is the events field is a field of the machine definition.
And how does that relate to?
And so this projected content template keyword says to just descend on that field and take whatever the content in that field is and project it using whatever projector is associated with that content. So if the events field contains events, then the project def for each of those events will be executed. And so that's where the relationship comes from into the project def for event.
So let's compile this and see what happens. Okay? In the interest of time here. So we now transforming this. It's this tree into a set machine. Here's Martin's example of the tree of that particular state machine. Or that
So this is kind of a free projection that you get if the program that you've written isn't loaded. As soon as it finishes compiling, it'll update with the projection from the code, the default projection.
This is here we go. So we're using the table projection here to just display this state machine. And we have a number of events, we have a number of commands, and so on. And here, of course, we can go through and look at some of the other projections. So why don't we look at the code projection?
Well,
So this is one of the examples that Martin had in his example, but a more concise and textual DSL for the state machines. And we use Ruby style syntax. And for people that likes XML, we have that option too.
yeah, very important to have the XML version.
Oh. And let's look at the graphical projection. Just go through, project the same thing through the graphs. And what else?
We can do
oh, right.
some C# code,
Well,
which looks a lot like the Java code, by the way.
traditional Java code, and then the Fluent.
So if you were to edit this right now, right, it would know how to project map back to the model itself.
Yeah, we can do some editing here.
Yeah.
We pick some edit in the Ruby notation, so we change just a simple thing that's alert panel, and let's go back to the.
What's that?
Just to project that in the graphical view, for instance.
Oh, yeah.
Oh, you have-
So we've changed the name of this command, and then, make sure I don't try to just there.
So, can I ask a question?
Yeah.
So there are things you can express in one of the projections that won't translate into others.
Right.
So for example, you could put perfectly valid Ruby code in there that wouldn't map at all. How would that translate? What would you do?
Yeah. So if you add Ruby code to it, right? So you can either use a Ruby elements in the tree itself, and then of course you decide in the graph projection.
I'm sorry, but if you go back to the Ruby projection.
Okay.
And then you can just put whatever Ruby code in there you like, right?
Yeah.
And then what happens when you go back to the state machine? Graphical projection.
Graphical. So in the graphical projection, we don't show any of the code. So it's still in the tree, but it's deleted from that particular
Yeah, it's hidden.
projection. It's up to you when you write the projections.
And
wanna
anything
show
that was actual Ruby intentions would continue to project as Ruby wherever it is in the document in the other projections that are more text-oriented. For example, I don't know if you've noticed, this paragraph about Miss Grant's controller has been sort of staying here the whole time, and it's actually not part of this domain at all. It's in a text editing domain that allows, for headings and paragraphs.
Can you mix projections? Like,
well, yeah, we're mixing. The question was, can you mix projections? We're mixing projections right here.
Text here.
This is a word processing type mini domain. This is the state machine.
so if I was writing stuff where, like part of it is